accidentally told it to record on the cloud, and I prefer it on my computer. Okay, so we are recording now. All right. Okay, so here is the plan for the rest of the school year. So today we're going to go over the answers to Friday's homework. I have already posted the practice test on Canvas. Some of you may have already seen it. If you have any questions about it, I'll be glad to talk about those. Today's session I'm expecting will be a relatively short one. Wednesday from 1 to 2 we'll go over the answers to the practice test. Friday there will not be any class. That's the day that I had planned to give the test, but based on your feedback I've now pushed that back to Monday from 1 until 3. And it is important that everybody does have to take the test at that same time, just like I've done on all my previous tests. So be sure to talk with your parents and your siblings and make sure that you have exclusive access to the computer on that day during those times. So that's a week from today from 1 until 3. I've got the test designed so that it would only take 90 minutes under normal circumstances. The reason I'm giving you some extra time is because part 2 of the test is going to be like I did last time, where you're going to work it out. Most of you are going to do it on paper. In fact, almost all of you. That's what you chose to do last time, was to do it on paper and then take a photograph and then upload the photograph. And I realized that taking the photograph and uploading the photograph takes time, and therefore I've given you an extra half hour in order to do that. And then after the test is over, please return your books to the school. If you have one of the old crappy books that's in terrible condition where I didn't ask you to bother signing it out, you can keep that book if you want. But if you're not planning on using the book, I would appreciate getting it back so that next year somebody could maybe take it and use it then. But if you want to keep it, fine. And if you have one of the new books where you did sign it out, then I definitely do need that back. If you want to keep it over the summer, you're welcome to do that. And I have received an email from one person asking to do that. And so I have notified Nancy not to put that person's name on the fines list. So if you want to do that, that's fine, but you got to tell me about it. Otherwise, your name will go on the fines list. Okay, any questions about the plan for the rest of the school year? Nope, okay. All right, well, let's talk about, well, first, before we go into the homework, let's talk about the quiz. Okay, if anybody got question number 1 wrong, I'm going to severely wag my finger at you, okay, because all this quantum mechanics and relativity stuff that we've been doing is most definitely not a bunch of bovine excrement. It is very much real, okay? Okay, and then, so then the problem with the saying that the mass causes the fabric of the universe to be stretched, the problem is not that the fabric of the universe is stretched near a massive object, because that is in fact true. The problem is the cause and effect here. It's not that mass causes the fabric to be stretched. It's the other way around. It's that the stretching of the fabric is what causes mass to exist. Okay, so that should be clear. Okay, so which one of them is special relativity? Well, the bottom one is. The others are very real effects, but those are effects of general relativity. Special relativity is exclusively for the weirdness that happens because you're moving at high speed. Okay, gravitational frame dragging, that's when you have the Earth and the Earth is spinning and it's dragging the fabric of the universe with it as it spins. And so that affects the motion of any objects that are close to the Earth. And the effect is very, very minimal. It's so minimal that you wouldn't even notice it for the moon. The effect on the moon is we just don't have equipment that is sensitive enough to measure it. But if we have some satellites, some artificial satellites that are in a close orbit to the Earth, then the effect on those satellites is measurable. It's still really, really small, but it is measurable. Okay, the test will be held a week from today. and the secret phrase was quark. And all of these other words that you see here, fermion, boson, hadron, lepton, those are all words that I had hoped that we would talk about this year. And if it weren't for the coronavirus, we would have talked about them. These are all subatomic particles. And I am not going to ask any questions on the test about any of these things, but I would hope that you would take a little bit of time and open up the book. And I don't remember which chapter it's in, but there is an entire chapter devoted to subatomic physics. And I personally think it's fascinating. And if it weren't for the coronavirus, we would have covered those this year. But what you gonna do? All right, so that's the quiz. Let's talk about last night's homework. So here are the answers to the problems from the homework. And as you can see, there was only one problem where you had to even get out your calculator at all. The rest of them were all just questions where you had to explain what something is or why something happens. So I'll give you a minute to look those over. Does anybody have any questions? Number 45, that's okay. We can definitely do number 45. Okay, let me see. I forget what the question was. It was, okay. I'm gonna have to go in here and open up the, let me see. If you can get to it faster than I can, more power to you. Let's see. Okay, I've almost got it here. Okay. Okay, so a 100-watt light bulb consumes 100 joules per second. How long could you burn that bulb if you use the energy from 1 penny? Okay, oh, good, Cohen, okay, you got it. All right, so let's, okay, so there's the question. Let's open up a white page. Okay, so the mass of the penny is 3 grams, all right? So we know E equals mc squared. So mass is 0.003. The speed of light is 3 times 10 to the 8th. I'm gonna have to square that. My calculator is not here. Hang on a sec while I go get it. Okay, so if I do 0.003 times 3 times 10 to the 8th, and that has to be squared, see, it has to be squared. Okay, so I get 2.7 times 10 to the 14th joules. All right, so the light bulb is using up power at a rate of 100 watts, and a watt is a joule per second. Okay, so that means every second it uses up 100 joules of energy. Okay, so if I want to know how many seconds of power I've got, I take 2.7 e to the 14. I want to divide that by 100. Okay, so I get 2.7 times 10 to the 12th. That's how many seconds of power I can get from taking a penny and converting it into energy. So that's a long, long, long time. So all I need to do then is just translate that into how many units that are units I can deal with. So if I want to know how many minutes it is, I divide it by 60. And if I want to know how many hours, I divide it by another 60. If I want to know how many days, I divide it by another 24. And if I want to know how many years, I divide it by 365. And when I'm done, I get about 86,000 years is how long we could run that light bulb. 86,000 years. Okay. All right, number 40. So I hope that's good there, Maddie. And so I'm going to go to number 40 now. So number 40 says, Would you age faster on the mountaintop or at sea level? Okay, well, remember that time slows down because your body is stressed. Okay, so either because you're being pushed through the fabric of the universe at high speed or because you're near a highly massive object. Okay, so if you're up on the mountain, the force of gravity there is ever so slightly different than it would be if you were down closer to the surface of the Earth. And so the higher you are, the less stress your body feels, and therefore the faster the clock is going to run. Okay, so Ellie, I hope that answers your question there about number 40. Does anybody else have any question? Okay, good. All right, so let's go back here to this, okay. All right, and let me make it full screen. Okay, so now nobody asked any questions about 10 or 12, the correspondence principle and the equivalence principle. So let me ask you about those, because I know from past experience, students always get them confused, because correspondence and equivalence are two words that have a lot of overlap, and so people get them confused. Okay, so the correspondence principle says that if you come up with a new law of physics, like for instance, the one example given here. So prior to Einstein coming along, everybody thought that F equaled ma was all there was. They thought that was the complete thing. But then Einstein comes along and says, no, that's not really true. The more complete version would be F equals ma divided by the square root of 1 minus v squared over c squared. Okay, well, the correspondence principle says that if this new equation is valid, it needs to also work back under the conditions where the old equation was valid. Okay, so the old equation, whenever we did any experiments with that, up until recently, all the experiments we did were always ones where things were moving at a speed that was way slower than the speed of light. So you see right here, it says, so if the velocity is a whole lot less than the speed of light, then I hope you guys agree that that means that the velocity squared is going to be a whole lot less than the speed of light squared. Okay, because if you take a small number and square it and a big number and square it, that big number gets a heck of a lot bigger than the small numbers. The big number squared is a heck of a lot bigger than the small number squared. Okay, so v squared over c squared is a number that's so close to zero under normal circumstances that it might as well be zero. And so then 1 minus that number is a number that's so close to 1 that it might as well be 1. The square root of 1 is, of course, 1. And so the new equation then reduces down to be exactly the same as the old equation if you apply the new equation under the conditions where the old equation was valid. Namely, the speed of the thing that you're dealing with is a whole lot less than the speed of light. Okay, so this is an example of the correspondence principle. The new law has to correspond to the old one under the old circumstances. Now, the equivalence principle says that the effects of gravity are equivalent or indistinguishable from the effects of accelerated motion. So you guys know the thought game that is my favorite game to play. So you go to sleep tonight in your own bed, but tomorrow morning you wake up in a metal room with metal floor, metal walls, metal ceiling, and a NASA logo on the wall. Okay, so you get up and you say, I wonder if I'm in outer space or what. And so you take some object, you drop it, you measure the acceleration, you find that it's 9.8 meters per second, and so you say, oh good, at least I know we're on the planet Earth. Well, maybe not. Okay, it is entirely possible that you could be, so look at the bottom picture here, hold off on the top one there, okay? It is entirely possible that you could be in a spaceship which is accelerating at the rate of 9.8 meters per second, okay? And what Einstein says is that there is no experiment that you could do that would distinguish between the effects of accelerated motion and the effects of gravity. They are exactly the same. And Einstein actually used this idea to derive some of the equations that he used, which we didn't talk about. But remember we said that the light got bent, and it got bent by the exact amount that Einstein predicted. Well, we didn't talk about the equations that Einstein used to predict how much that light would get bent. Okay, but this is how he came up with those equations. Is that he says, okay, if the effect of gravity is the same as accelerated motion, then we can use that connection to derive the equations. Now, I don't intend to derive those equations. I just want you to know that's how he did it. Okay, and then the upper picture here, you've got a light beam that is coming in through the window on the spaceship, but the spaceship is accelerating. So when that light beam reaches the midpoint here, you can see the window and the rest of the spaceship has moved up a little bit. And by the time the light beam gets to the far wall, that window has moved up some more. So a person on the outside looking in, they would say, well, that light ray is just going in a straight line. But the person on the inside, they don't know that they're accelerating. They think that maybe they're just in a gravitational field. And so they are going to see that light ray bending downward. They're going to see that light ray behaving as if the gravity was pulling it down. And so the equivalence principle says that the two are indistinguishable. So be careful, because this is something that I might put on the test. And it's easy to get the equivalence principle and the correspondence principle mixed up. So I would recommend you put that on your cheat sheet so that you don't get it mixed up. Okay, so back to last night's homework. Last chance, are there any questions about last night's homework that we did not talk about? Okay, I'm not seeing any questions. All right. So there are a few interesting things that I want to just mention in briefly. You got to promise that you're not going to tell Mr. Wilson that I'm giving you any new material here. He might get upset at me. He might wag his finger at me. And boy, you do not want to be on the receiving end of a Wilson wag. Scandal, yes, I agree. Okay. So when you read when you read the handout on general relativity, there's one idea that they talked about in the handout, which I did not talk about myself, but I'm hoping that you read it. And I just want to make sure that we spend a few minutes talking about it, because it is important. Okay, so they talked about a new geometry of space. And this is terminology that confuses a lot of people. How can space have geometry? Some people say, well, space is flat. Other people say, well, no, it's got positive curvature. Or other people say, no, it's got negative curvature. And how can space be flat or have curvature? Well, there actually is a good way to understand that. Okay, so the way that I recommend we approach it is this. Let me ask you guys, if you have a triangle, any triangle, okay, if you add up all three of the angles of the triangle, what number must you get? Somebody type in the answer here. Ellie says 180, Teresa says 180. So it looks like everybody agrees it's 180. Are you sure? Okay. Now, a lot of you are probably saying, well, if anybody other than Mr. Hendricks had asked that question, I would have said 180. But if Mr. Hendricks is asking it, then I'm worried. Okay, and well, you should be. Okay, so Cohen got the right idea here. So he has just typed in that it's 180 in Euclidean space. So let's find out what Cohen means by that. Okay, what if instead of drawing that triangle on a piece of paper, you draw that triangle on the surface of the planet Earth? Okay, so the picture that you see in the lower right here, it's a triangle. It's got three angles, right? Yeah, aha. So Josh, yes, I am getting that. So Josh just said, hey, wait a minute, isn't the Earth flat? This is a good way to determine whether or not the Earth is flat. Back at the beginning of the school year, when I asked you guys for ideas on how you could prove that the Earth is not flat, this is one that nobody mentioned that we could have used. We could have done a simple experiment here to find out if the Earth is flat. Now, we would have had to leave the boundaries of the state of Utah in order to do this experiment. Therefore, I didn't allow it back then, but I will allow it now. Okay, so let's suppose that we think the Earth is flat. Okay, so we're going to do an experiment. We're going to start off right here at the North Pole, which my flat Earth friends, they think is in the center of the disk. Remember, the Earth is a flat disk. Okay, so if you start at the North Pole and you walk in a straight line, as far as you know, it's straight, and you walk south until you get to the equator, and then you make a 90-degree turn to the left. Okay, and then you walk the exact same distance that you just finished walking. So from the pole to the equator, you measure that distance, you count how many steps it took you, okay? And then you walk the same number of steps, okay, after you've turned 90 degrees, okay? You then make another 90-degree turn, okay? And then you start walking back up north again. So you've already violated the sum of the triangles, because you can see here that you've already got 90 degrees plus 90 degrees. There's 180 degrees right there, and you have not yet gone back to your starting point. So if you do what we said, then when you get back to the starting point, you find that in order to retrace your path, you would have to turn another 90 degrees. So what you've just done is you have just effectively drawn a triangle on the surface of the Earth. And if you add up the angles of the triangle that you just drew, you find out that it comes to an angle, it comes out to be a number that is greater than 180 degrees. In this case, it's 270. Okay. Now, if you drew a smaller triangle, you know, if instead of walking all the way from the pole to the equator, if you had only walked a smaller amount, and then a smaller amount here, then the total of the three angles would come out to be less than 270, but it would still be more than 90. Okay, so by drawing a triangle on what you thought was a flat surface and measuring the angles, and when you see that they come up to a number that is not 180 degrees, you've just proved that the Earth is not flat. Okay. Now, here's where it's interesting. If the number that you get when you add up the three angles is greater than 180, then we say that the space that you are in has positive curvature. If the angles turn out to be less than 180 degrees, then we say that it's negative curvature. So when you go up here on the book here, so this is taken from the handout that you guys read, okay? So if it's flat, you get 180. If it's a surface that looks like this, which is like this, the Earth, okay, then you get a number greater than 180. And if it's a saddle kind of like thing here, then you would get a number that's less than 180. Okay, but the important thing is that it turns out to be not 180, therefore you know that space is not flat. Okay, so Cohen called it Euclidean space, and so he was exactly right. So Euclidean geometry is any geometry that is done on a flat surface, a piece of paper that, you know, a flat piece of paper, not a bent piece of paper. Whereas non-Euclidean geometry is done like this. Now, you guys have heard me say many, many, many times that the best way to learn physics is to go sailing. Well, sailors need to deal with this. If you're a sailor and you're doing celestial navigation, when you get out your sextant and you measure the angle, you have to do a bunch of math. The math that you do consists of drawing little circles, at least in your mind, drawing circles on the surface of the planet Earth and then solving using the law of cosines and using Pythagorean theorem and all those things, except that the Pythagorean theorem that you guys know doesn't work in non-Euclidean space. You have to have a modified Pythagorean theorem. And same thing with the law of cosines. The law of cosines that you guys know, you know, a squared equals b squared plus c squared minus 2ab cos bc, okay? That doesn't work if you're working with non-Euclidean. Okay, it only works with Euclidean. All right, so I'm being told that the video stopped for a second. All I can, okay, so several people say it got frozen. It's back working again now? Okay. All right. So let me go back and just restate what I just said. Okay. So uh, if you are a sailor, and if you're figuring out your latitude and longitude by measuring the angle of the stars and doing some math, the math that you do is geometry, but it's non-Euclidean geometry, because the circles or the triangles that you need to do when you're doing the math are triangles that are drawn on the surface of the earth, not triangles that are done on a flat piece of paper. So in the process of doing the math, after you've measured the angle of 3 different stars, the math that you do, you have to use things like, for instance, the law of cosines. So you guys hopefully remember the law of cosines, right? So it says c squared equals a squared plus b squared minus 2ab cosine of angle C. Okay, well, that law of cosines only works for Euclidean geometry. Now, there is a version of the law of cosines that is similar to, but not the same as, the law of cosines that you guys are familiar with. So if you're a sailor, you need to know non-Euclidean geometry, at least if you're going to do celestial navigation, which very few sailors can do. And don't worry, I'm not going to make you guys do it. So I just want you to know what people are talking about when they ask the question, is the universe flat or is the universe curved? Okay. And here is an example of something that we could do that would prove that the universe is not flat, at least not if you're anywhere near an object that has mass. So what I've done here, so where I've got my cursor right now, imagine that that's a person who has 2 laser pointers. So there's this person, and this person has her 2 friends, like this. Okay, so she is going to take her laser pointers, and she's going to adjust her laser pointer until one laser pointer hits her friend right square in the chest right here. Okay, and she's going to twist, she's going to adjust the laser pointer until she sees that the dot appears right on her friend. She's going to do the same thing over here. She's got this other laser pointer, okay, and she adjusts it until it lands right on her friend. And so then what she does is she measures the angle between the 2 laser pointers. And the friend over here is doing the exact same thing, and the friend over here is doing the exact same thing. So all 3 of them are going to measure the angle between the laser pointer that's pointed at the one friend and the laser pointer that's pointed at the other friend. They're going to measure the angle. And when they take those 3 angles and they add them up, if they get a number that is greater than 180, that means that space is curved. Space is not flat. And in fact, that is exactly what happens if in the middle of our triangle here we have a massive object. We will find that the number we get adds up to be greater than 180 degrees. So then we would say that space has positive curvature, at least the space that is near a massive object. Now, if you did this same experiment where you didn't have a massive object there, okay, then things would be different. All right, so I just wanted to talk about that because it was in the handout, but I'm willing to bet a large sum of money that many, if not most of you, did not understand it if you even read it at all. Okay, now, there's one other thing that we need to talk about because it is very important, it's really cool, and it's quick and easy to understand. Let's suppose that you are one of my friends in the Flat Earth Society, and so you are fixated on the idea that the Earth is flat. And so then you and a person who is not a member of the Flat Earth Society, you both need to make a journey. Let's say you're going from Salt Lake City to Moscow, okay, in Russia, right? So the 2 people both need to make a journey to get to Moscow. And let's say that you are good law-abiding citizens, so you don't want to violate any speed limits, okay? And so you're going to drive there, which is going to be a little tricky if you're going to cross the ocean, but let's not worry about that. Let's suppose that there is a highway, so you could drive, but you don't want to break the speed limit, okay? So the flat earther, they are going to have to go along the surface of the earth. And now they are going to go in what they say is a straight line. They're going to point their car And if they get the wheel pointed just right, they can make this entire journey without ever once touching the steering wheel. Okay. Now they're going to have to get the steering wheel exactly right, but in theory it could be done. That I don't think so. I just see a recording asking if or a question asking the recording stopped. No, the recording's still going. Okay. All right. So the flat earther, they make the trip in what they are convinced is a straight line. But the person who's not a flat earther, they have an advantage. They realize that the earth is not actually flat. They realize that there is a faster way to get there without violating the speed limit. Okay. Because they know that the earth is not flat, what they can do is they can drill a tunnel which connects Salt Lake City and Moscow in a straight line that really truly is straight. Okay. And so they can make it from Salt Lake City to Moscow in less time because they are going less distance. Now it only works if the earth is not flat. If the earth is flat, then this wormhole is not going to, or I'm not sure if I said that right. Let me say it again. If the earth is flat, then this wormhole trick is not going to buy us anything because the yellow line and the orange line will be the same length. So this wormhole trick only works if the earth is not flat, okay? All right, so we can get there faster. All right, so I'm sure you guys have heard about wormholes. There's lots of science fiction movies where they talk about wormholes, including the movie that we talked about last time, Interstellar. They take advantage of wormholes there. Okay, so the idea is that if the universe is not quote unquote flat, according to the definition that we've just got through talking about, okay, then a person who thinks that the earth, or a person who thinks that the universe is flat, if they want to get from point A up here to point B down there, they would have to go the long way around. Whereas a person who somehow knows that the universe is not really flat, okay, they might possibly be able to drill a hole here and get from point A to point B by taking this shortcut. Okay. Now they're not going to violate the laws of physics. They're not going to travel faster than the speed of light or anything like that. But they are going to get there a lot faster than their friend who goes the long way around. Okay. So this is the wormhole that I know you guys have heard so much about in science fiction movies or whatever. So wormholes could possibly exist, but only if the universe is not flat, which we have seen that the universe is not flat near a massive object. So what's the most massive object that you can think of? A black hole. So a black hole then is the best candidate for if you're searching for wormholes that might allow you to go from one place to another place. Maybe if you go through a black hole, who knows what you might find on the other side, provided you survive the journey, which I doubt very much that you would. Yes, death is what you would find on the other side. I agree with you on that one, Joshua. Okay, so Jaron is saying that we imagine space as flat because we cannot see a fourth dimension. Yeah, I agree with you. Have any of you ever heard of a book? It's actually a booklet. It's a very short booklet. It's called Flatland. It is okay, so some of you have heard it, good. I don't want to take, I'm not really able to take the time right now to talk about it. Google the term flatland, okay? And then read what you see there. It's a fascinating little booklet that talks with people who live in a two-dimensional world, and their eyes are not capable of looking up or down. Their eyes are only capable of looking in the plane of their two-dimensional world. And so along comes a three-dimensional object, which is up above. And if that three-dimensional object comes down from above and it starts to intersect with their world, then these two-dimensional flatlanders, they are going to be astonished. They're going to say that an object appeared out of nowhere and and then as it continued on past, then it then disappeared nowhere. And they are going to be totally astonished. They're going to say the laws of physics have just been violated, but not really, because we know that the Earth is actually three-dimensional, not two-dimensional. And so when this object comes from above and touches their plane and then passes through it, okay, not violating any physics at all. So the idea here is that maybe the universe is not a three-dimensional universe. Maybe there's a fourth, fifth, or sixth dimension. And when I say that, do not tell me, oh, well, the fourth dimension is time. No, that's not what I mean. I'm talking about spatial dimensions, okay? A fourth spatial dimension that we, with our limited minds, we cannot conceive of it, just like the Flatlanders could not possibly conceive of a three-dimensional universe. And so Jaron is asking about tesseracts. Yeah, that's kind of the idea behind a tesseract, at least as far as I understand the term tesseract. Although I'm not really big into these movies that feature tesseracts. I started watching one. In fact, just this weekend I started watching one, but it just got too boring, so I quit it. Okay, so that's it for today. If you have any questions, go ahead and type in your questions. And while I'm waiting for you to type questions, let's just talk about the homework tonight. So the practice test has already been posted on Canvas. So if you haven't already downloaded it, go ahead and download it. And so the rules on the practice test are going to be the same as they've always been. If you spend at least an honest hour working on it, then you can give yourself a 9 out of a possible 10 points on Wednesday when I look at the submissions. But obviously, if you haven't done the entire practice test, then you're not going to be as well prepared for next Monday's test as you should be. So I would certainly recommend spending more than an hour on it, but I'll give you 9 out of 10. Did I spell Hendricks wrong? I don't understand your comment then. Doesn't make it Hendricks. Oh, for the secret word. Ah, okay. Well, yeah, we could do that. I'd be willing to do that. Okay, so that's your homework for tonight, and there will be a daily quiz today. It'll be a really simple quiz, just purely conceptual. If you were paying any attention at all to what I've just talked about for the last half hour, you'll have no trouble. Okay, so the secret word for today is going to be Hendricks. And so that's about it. Any questions before I start the countdown? I'm not seeing any questions, so here goes the countdown. Going once. Going twice. Sold. Okay, I'll stop the recording. Goodbye, recording.